Okay, guys, now let's start working through an example problem. This is going to be a bit tricky, but if you're able to solve these kinds of exam problems, I guarantee you will be able to solve anything thrown at you at any exam. So let's roll our sleeves up and get to it together. In this example, we are going to analyze a vapor compression heat pump process. Using thermodynamic property tables. So at this stage, we are only defining the system and the given data. We're not calculating anything yet, but before that, the first task, if you will, is to find the information in the property tables. First, the working fluid in this heat pump is the refrigerant R134A, which is a commonly used refrigerant, and we will use property tables for R138 throughout the whole example here. Next, we are given the operating temperatures of the heat exchangers. So for the evaporator temperature, that's minus 22 degrees of Celsius, and this is the temperature at which heat is absorbed from the cold source. So that's going to be around here in state 1 for the example problem here. Then the condenser temperature is 28 degrees of Celsius. This is the temperature at which heat is rejected to the surroundings. So that's going to be here on the diagram. So that's we can connect it to state 3, and we can connect that one to state 1. So the next information that we are given is the state of the refrigerant. That is given in the two sentences here. So the refrigerant leaves the evaporator as saturated vapor, and the refrigerant leaves the condenser as saturated liquid. So these two sentences, they tell us what kind of property tables that we have to look up to get the states. So for state 1 and state 3, which is over here and over here, those states are going to be really easy to find because we know the temperatures and we know what kind of tables that we need to look at. So I'm going to give you the tables so you don't have to practice the lookup, but I'll just tell you what kind of tables you would have to look up at your exam. Then we know the isentropic efficiency of the compressor, which is equal to 75%. This means that the real compression requires more work than the ideal isentropic compression, and we must account for this when we determine state 2. And that's the tricky part here, because this is the only thing that we have been given, so nothing about state 2 and nothing about state 4. State 4, however, as you know, is going to be equal to one of the other states. If you remember what we talked about, we're going to get back to that part when we get to state 4, but the tricky part here in this exam problem, and the reason why this is a very tricky exam problem, is that we need to find state 2 by utilizing the ideal version of the compressor. So getting here to state 2, that can be a little bit tricky, but I'm going to show you that trick. So the whole exam problem here, or the typical exam question, is that they want you to determine the coefficient of performance, COP, of the process both for heating and for cooling by using thermodynamic tables. We could have used diagrams as well, but now we are using the tables. Okay, the first step that we'll take is to determine state 1 to find the properties that we're looking for here. So we'll start the example by defining that. So state 1 corresponds to the outlet of the evaporator and the inlet to the compressor. So everything we do later depends on getting this state right. So it's important to be precise here. So at state 1, the temperature were given at minus 18 degrees of Celsius. And therefore T1 equals minus 18 degrees of Celsius. We were also we looked at the part here that the refrigerant was saturated vapor. That means that the quality is equal to 1. So we could write down the quality also. But we won't need it, especially for now, or in this example problem. Just it doesn't matter. Let's just keep it there. But the sentence was that we had saturated vapor. So at state 1, the refrigerant is just leaving the evaporator fully vaporized and at the evaporator temperature. So that means that we have to find the tables that corresponds to properties of saturated refrigerant of 134A, which is liquid vapor. That's the critical part here, that we find these values. And when we look into the table here, we can find minus 18 degrees here. So we know that somewhere along this row here, there will be some values that we need to grab and bring with us to the next one. The most obvious value that we need is the enthalpy. So H1 is something that we need to grab. We know that the refrigerant at this state is saturated vapor. So that means that we need to find the enthalpy for saturated vapor. The enthalpy options here are within these three here. So we have saturated liquid here. Then we have vaporized, and then we have saturated vapor on this column here. So therefore we need to go down into the part or the row at minus 18 degrees of Celsius and grab that value here. So being saturated vapor, H1 is equal to 237.53 kilojoules per kilogram. Okay, now we have found H1 and we have everything that we need from state 1 accordingly to being able to solve the COP for heating and cooling, but we need to grab something else that we can later on use for the unknown state of state 2. So in addition to the enthalpy here, let's grab the saturated vapor, because we're in saturated vapor, entropy as well. So we find a G here and this value as well. So the entropy of state 1 is equal to 0.9356 kilojoules per kilogram per kmol. So that was another property that we'll need to bring with us, and also one last value, and that is the pressure. So the reason that we need to grab or bring with us the pressure is that we'll utilize it to find state 2, because that's the tricky part. So the pressure here, 1.4552 bar. Pressure 1 is equal to 1.4552 bar. That's going to be important for us to have when we look at state 2 in a second. So from state 1, we have these values that we're going to utilize to find state 2. Okay. I think I have emphasized that enough now, so let's find the other obvious state, or the other easy part of the exam problem here, which is state 3, because we have given all the information. And we do this first because it's convenient. So we'll get some values here that we can use later on. So state 3 is the outlet of the condenser, and its thermodynamic state is directly specified in the exam problem data. So at state 3, we had temperature of 28 degrees of Celsius. And the refrigerant is saturated liquid, so the quality is equal to 0. So at state 3, the refrigerant has fully condensed, no vapor present, and is exactly at the condenser temperature. So because state 3 is a saturated liquid at a known temperature, we again use the saturated saturated R134A temperature table. So all the properties at state 3 can be directly read from the saturated table at 28 degrees of Celsius right here. So we'll bring with us the same values, but now we have saturated liquid. So we need to be specific about or think about the values or the properties that we choose from the table. Now let's just take the pressure here first. So pressure of state 3 is equal to 7.3038 bar. And then we can move on to enthalpy, which is between those three here. But now we won't choose the saturated vapor because we are now dealing with saturated liquid. So saturated liquid was on this column here. And then we move down and we find this value here. So H3 is equal to 89.05 kilojoules per kilogram. And the same for entropy. We aren't looking at saturated vapor now, but saturated liquid. So we have to choose this column here, move down until we find the value. So the entropy for state 3 is equal to 0.33185 kilojoules per kilogram per kmol. So defining state 3 now is helpful because it immediately gives us the condenser pressure and will also be calculating that pressure from the compressor outlet pressure. So this simplifies the compression analysis. So it's a strategic choice, not a conceptual one, if you will. So at state 3 now, we know the temperature, phase, pressure, enthalpy, and entropy. So it's fully defined. And next we can use this information to move toward a compression process, starting from state 1 and working up to state 2. But to find state 2, we have to do something that can be hard to understand first, but I'll try to keep it as simple as possible. So next, when we want to define state 2, we have to utilize what we call state 2s. And that means that we represent state 2 utilizing the ideal outlet state of the compressor, assuming isentropic compression. So we introduce this state so we can later account for the compressor efficiency. So the compressor outlet pressure must be the same as the condenser pressure. Since the condenser is modeled as an ideal heat exchanger with negligible pressure drop, then the pressure remains constant from state 2 to state 3. That is the first thing that's kind of hard to understand, but just keep it in mind and you'll understand it as we go through the example problem here. So the pressure in state 2 is equal to the pressure in state 3, and we just found that pressure. And then the entropy at state 2 or at state 2s corresponds to the isentropic compression. And in isentropic compression, entropy remains constant during the ideal process. So you can see that here from state 1 to state 2, entropy has a vertical line straight upward, so that process remains constant. That means that from state 1 to state 2, the entropy is constant, and we can write S2S equals S1, which is this value here that we found in state 1. So now we need to determine the specific enthalpy at state 2s, and at this point we know the pressure and we know the entropy. So when we go to the superheated tables, we can look for the enthalpy value that corresponds to the pressure and entropy, but we won't find the exact value. That's almost impossible in an engineering problem. So we have to interpolate in the tables. So because the pressure will be, so if we find the entropy on the left side here, on the pressure of 7 bar, because we are dealing in between 7 and 8 bar, so I have taken out these tables. We are dealing with a entropy of 0.935C6, and that is between these two values here, and therefore we need to grab these two values and these two enthalpy values, and we will utilize this value, this value, this value, and this value, and this value here, S2S, to interpolate. And we have to do the exact same for the pressure at 8 bar because we're dealing with a pressure at 7.3 bar. So in reality, we are interpolating between the pressure of 7 and 8, but also the entropy. So when we find the entropy here, that's between this value and this value. So we have to grab these 4 values as well. The enthalpy here and the entropy here. So we are doing it double up. So that's the tricky part here, and probably something that your examiner or your teacher is going to throw at you. But now I'm going to teach you all their dirty tricks, so you'll be able to fight back and get an A on that exam. So we are interpolating between the pressure of 7 and the pressure of 8, and we are also interpolating between the entropy, the S2S, in both terms here. So within the different tables here, we're trying to find the entropy here. So the pressure is between the tabulated pressures, and the entropy doesn't exactly match a tabulated value, so we must double linear interpolate. That's the thing, that's the tricky part that we need to perform here. So this is purely a numerical step based on the tables, and at this stage the important thing isn't the arithmetic but the method, so the fixed pressure, the fixed entropy, and to interpolate to find the corresponding enthalpy. So it's important to emphasize why we're doing this, and state 2s, which is the ideal state, not the real state, finding this allows us to compare ideal compression with real compression because we know that formula. So later, after we've double linear interpolated here, we can apply the isentropic efficiency of the compressor by utilizing that formula. Okay, so I think it's going to be too much information on one slide, so let's start with double linearly interpolate for the 7 bar table. So we're going to define the age to, let's call it A for 7. That's going to be easier for you guys to remember. So age to A for the first tabulated value, that's equal to age to A and the first value plus age to A and the second value minus age to A and the first value. Oops, that became a delta, not an A. And then we use the entropy that we also grabbed at that point for the B value minus the entropy that we grabbed at that point minus the A value. This is becoming too large as I see now, so let's bring it over here. And then we multiply by the entropy of state 2 minus our S2S minus S2A A. So plugging in the numbers here, the H2A that we need to find first is 267.70, using that value now, plus 2 267.31. That's this value here. Minus 267.70. All divided by 0.95867. That's this value. 0.95867 minus 0.9243. 0.92430. So that's these values here. And then we will utilize this value. Let's just bring it a little bit smaller. A little bit more. So then we will multiply it by that value, 0.93566. That's this value here. Minus 0.924324330. And the result here at 7 bar is equal to, so H2A, let's just write now, 7 bar is equal to 270.9 kilojoules per kilogram. So the first enthalpy of state 2s is 270.9 kilojoules per kilogram. Now we do the exact same for the 8 bar table. So you can try to calculate that by yourself. Just pause the video now and unpause it. So try to do that by yourself. It's the exact same same procedure as 7 bar. Okay, now you have probably tried to do this by yourself, so I'll just go through it. H2, let's call it B for 8 bar is equal to H2B, first value A, plus H2B, H2B and the B value minus H2B and the first value A, and then divided by the entropy of 2B, second value B, minus the S2B, first value A. All this multiplied by S2S, that's this value here, and minus S2B A, first value, entropy. Plugging in the numbers here, that makes for H2B equals 265.4 265.47, that's this value. Going to write circles instead. Then plus 275.03, that's this value, minus 265.47 divided by 0.942 of 7, that's this value here, minus 0.91113. That's this value here. And then we multiply by the entropy again. That's 0.9357. Or let's do it all the way. So that will be minus 0.91113. And the result at 8 bar, let's write H2B at 8 bar. That's equal to 273.1 kilojoules per kilogram. So then we have H2A 7 bar, that's 270.9, and H2B 8 bar, 273.1. Then we can start to finish up the double linear interpolation, and the formula here is going to be H2, and then the entropy here is what we're looking for, is equal to H2A plus H2B minus H2A divided by P2B minus P2A is equal to P2 minus P2A. So H2S is equal, or the enthalpy of state 2S. I think I said entropy in a second, I don't know. But it's the enthalpy, of course, so that's equal to H2A, that was 270.9 plus 273.1 minus 270.9. So 273.1, that's here, and 270.9, that's here. So that's these two values here. And then we divide by the pressure. So pressure of B, we said that that was 8.0 bar, and A was 7.0 bar. And then we multiply by pressure 2, that's equal to that pressure, 7.3038 minus the original pressure, which is P2A, that's 7.0 bar. Then the enthalpy of state 2S is equal to 271.6 kilojoules per kilogram. So when we have the kind of the, not the fake enthalpy, but the ideal enthalpy, then we can utilize the thermal efficiency of the compressor to find the real enthalpy, or H2, which is what we're looking for. So we want to find H2. Still, we want to find that value. But now we have all the values that we need to calculate that value. So the actual outlet state of the compressor, up to this point, we have defined state 1 at the compressor inlet, defined state 2S at the ideal isentropic outlet state, and now we connect these two using the isentropic efficiency of the compressor. So the isentropic efficiency of the compressor is defined as the ideal enthalpy rise divided by the real enthalpy rise. So that's this here. So the equation tells us how much extra enthalpy rise is required in the real process compared to the ideal process. Then we can solve for the real outlet enthalpy, which is the thing that we're trying to find out. So H2 is equal to H1, which is 237.53. That's what we found. So H1 is equal to 237.53. That's what we found in the first state. Then H2S is equal to 271.6. So that's going to be plus 271.6 kilojoules per kilogram. And then minus H1 again, so 237.53. And then divided by the thermal efficiency. And the thermal efficiency was something that we were given, or the compressor efficiency were given at 75% at the start. So this part here is equal to 0.75. So that's 0.75. Solving this, or crunching the numbers, that gives us 282.96. And we can also write H2 is equal to 283.0 kilojoules per kilogram. So now we have H2. And by this part, we have almost done everything that is hard in this exam problem. So we have done the tricky part, and now we can just utilize formulas and equations without so much thinking to kind of sum up the stuff that we have already found. So at state 4, that's going to be one of the most easy part of the whole exam problem, because state 4 is the outlet of the expansion valve and the inlet of the evaporator. So after the valve, the pressure must be the same as the evaporator pressure. So we have talked about that as well. So P4 is equal to P1, which is equal to 1.4552. And the key assumption for the expansion valve is that the process is isenthalpic. So isenthalpic. That's the key word here that makes this so easy for us, because that means that the enthalpy doesn't change. And if the enthalpy doesn't change, that means that we know the enthalpy. So from state 3 to state 4, the enthalpy remains the same. That means that H4 is equal to H3. And H3 was equal to, let's see, that was equal to 89, wasn't it? Let's go back to state 3 to be absolutely sure. Yeah, 89.05. So the enthalpy of state 4 is equal to 89.05 kilojoules per kilogram. So now we have all the values that we need to find the COP for heating and for cooling. So the performance factor for heating mode is equal to the COP for, used as a heat pump. That is equal to H2 minus H3 divided by H2 minus H1. So this essentially says that useful heat delivered has to be divided by the required work input. So from the energy balances of the components, the released heat, or Q out, is equal to H2 minus H3, and the compressor work, so the work of the compressor, is equal to H2 minus H1. So that's what the COP of the heat pump is essentially saying to us. Then we don't have to do much else than just plug in the numbers here. So to find the COP, or the performance factor for heating mode, that means that we plug in 282.96 minus 89.05 divided by 282.96 minus 237.53. And all of this is equal to 4.27. So that means that for every kilojoule of for every 1 kilojoule of compressor work, the system delivers 4.27 kilojoules of heat. So that's a pretty good COP for a heating pump. So this is why heat pumps are much more efficient than direct electric heating. Now we have found the COP for the heating mode, or the machine used in terms of a heat pump. The other question was to find the performance factor for the cooling mode. So how efficiently does the machine cool? So for cooling, COP as a refrigerant is equal to H1 minus H4 divided by H2 minus H1. So that means Q in divided by V net. So, or Q in divided by the work done by the compressor. And as you guys know, Q in is equal to H1 minus H4, and the work done by the compressor is H2 minus H1. So the only difference here is the Q in or Q out. Depends on what we're using the machine for. We have all the properties here, so we can just plug in the numbers. So the COP for the heat pump in cooling mode, or the machine in cooling mode, that's equal to 237.53 minus 89.05 divided by 282.96 minus 237.53. So the COP for a refrigerant or refrigerator purpose or air conditioner in cooling mode is equal to 3.27. So that means that for every 1 kilojoule of work input gives or removes, it's more correct to say remove heat, or remove 3.27 kilojoules of heat from the cooled space. So that's the final part of this example problem. We have utilized some tricky stuff that once you now get this thrown at you, maybe in a tricky exam question, this is going to be much more solvable for you. So just remember that when you have a state that isn't fully defined, we can think about the ideal state and then utilize the formula to kind of translate that state into the state that you want. Rearranged the equation here. So that was the most tricky part of this whole exam question. Before we end this section, I just want to quickly touch on the process improvements of the vapor compression cycle. So we'll do that in the next video. Thank you guys for this one. I'll see you in the next one.